This is a car, and this is the engine of the car. As the engine churns, it sends filtered gases through each of its pistons and harnesses mechanical energy through combustion. The resulting gases of that combustion come out here at the exhaust. That nasty exhaust is made up of what's known as constituents, gases like carbon monoxide, nitrogen oxides, sulfur dioxides, really all your ides. But perhaps the most harmful and alarming of those ides is carbon dioxide emission, a greenhouse gas. In fact, carbon dioxide comprises almost 75% of greenhouse gas emissions, making it the lead human contributor to climate change. Canada ourselves being responsible for around a 50th of those emissions, which is a considerable amount. While certain policies and government intervention have started the slow decline of CO2 emissions, the problem remains a lot of our everyday appliances and devices emit carbon dioxide. This fireplace is a very evident example, but a lot of other things like a gas stove or a fridge in your kitchen, right here in this furnace room, is a pretty big emitter of CO2 in residential households or outside from your lawnmower to your grill. It's something we see every day, and it really needs a big change before we can start seeing a drop in CO2 emissions.
Water is our most abundant resource. Covering 71% of the Earth's surface, water is in many cultures and philosophies a symbol of life. What if we could use this natural source of energy for our everyday appliances? Well, combustion doesn't have to release greenhouse gases.
So how are we going to generate combustion in an engine without using gas? Well, we won't be using gas per se, we will be using a gas, hydrogen, generated from a clean energy source, water. The very basis of this research stems from electrolysis, which is the separation of water via electricity to hydrogen and oxygen, or in other words, an HHO generator. So if we set up an electric field like this, and there's water in here, and the water is diluted with sodium hydroxide, its very basis, the water molecule will be arranged like so. And again, very simply, there will be a reduction at the cathode, where the liquid water will take on 2 electrons and separate the hydrogen gas and the hydroxide ions, which become aqueous. This has a much more favorable cell potential than if a sodium ion were to just take on an electron, because this is around 2.7 volts, I believe, where this is around 0.8. But even when this does happen, the aqueous sodium will, the aqueous sodium will actually just react with water pretty violently, as these metals do, to produce just even more hydrogen gas and sodium hydroxide as a byproduct. So either way, at the anode, we're generating hydrogen gas. And then at the cathode, there is the oxidization reaction, of course. And water will be a byproduct of this half reaction of the hydroxide with the electrons. And 4 electrons. So this is multiplying the reaction by 2. And then when we do that, we can combine these two reactions, and rule out the electrons to get 2H2O liquid, which will convert to 2 hydrogen gases at the cathode, and oxygen gas at the anode. So this is very simply the concept of electrolysis. You put a cell potential between here, a certain voltage that's greater than 2.7 volts, let's say, at the very minimum, and it will separate the hydrogen, bring it over here, and the oxygen, bring it over here. These can bubble up through here if this is the up direction, and the hydrogen can be collected. And once the hydrogen undergoes combustion with oxygen in the air, or even oxygen from this part of the electrolysis chamber, it'll just condense back down to water, which can go back right into the into the electrolysis. So this is, in theory, a sustainable method of combustion, but of course it's more applicable to have a constantly refilling amount of electrolyte-filled water as sort of your tank of gas. So a lot of current attempts at electrolysis involve some form of cell or container with a vertical, this will be a circular container, with a circular anode and a circular cathode, sort of like screws. Often they are screws. And this would create the electric field between here. And you would have sodium hydroxide in the water, and you can have hydrogen bubble up through through here. Sorry, hydrogen bubble up through here. You can extract this and use it in a combustion chamber. However, there is a slight problem with that, and it's the reason this technology hasn't been adapted yet, and it's that compared to gas, the electrical energy that you are putting into the electrolysis is obviously it's not going to be equal to the energy you get out, but it's such a lower amount, the energy you get out, that it's more cost effective to go with gas. So the goal is to make this water electrolysis more cost effective than gas so it can be adapted. The issue with some of these is if you look at that chamber from the top down, so you have the anode and the cathode. It's sort of this circular chamber that all the water is in. And we take a look at the field lines. From here to here, it's uniform, kind of like the diagram we saw earlier when we were talking about the electrolysis. However, as it curves around, the divergence of the electric field, which is denoted as such, will actually decrease. It'll be lower than 1. Because the curl is increasing and you have to curve more to get to this negative cathode. And because of that, a lower electric force will be applied towards this direction on whatever molecules. On the hydrogen and the oxygen molecules within the electrolyte infused solution. So this is a pretty big inefficiency, because especially when you're considering this outer shell over here, and you have some H2O molecule here, it's going to take a lot more effort to sort of swing it around there, a lot more electrical potential energy to separate this molecule than it would for a molecule in here, where the divergence is 1. So how can we create a uniform electric field and use it for hydrolysis in an even manner? This is the basis of my proposed research. If you have a small copper tube in the middle, acting as a cathode, and a larger copper tube surrounding it, let me draw that, and a larger copper tube surrounding it, that is a cathode, then you will have a uniform electric field over here, where the divergence is always equal to 1. And the electric field potential is a lot more even and efficient. In this case, because it's more efficient and the hydrogen will move out over here, you'll get hydrogen gas here and oxygen gas here. Not only is it much easier to collect from 2 different sort of inner and outer stages, it's much easier to collect those gases, but obviously the uniform electric field will create a much more efficient hydrolysis chamber. So with that in mind, let's take a look at some preemptive design.
Okay, so after having tested out the low divergence design with a Gatorade bottle and making little balloons of explosive hydrogen gas, I took to design a model that leverages divergence, which you can see over here on Fusion 360. If we take off this bottom here, you can take a look at the electrodes. So this would be the anode where the hydrogen would collect, and this is the anode. And if you look at it from a bottom-up perspective, you can see that this would absolutely be a uniform electric field. You could connect it to a power supply from the top here for experimental purposes. If you look at these caps, they act as sort of plugs where you could solder on a wire to connect to a power supply. And over here you can see for the anode, it's connected only by these 2 clips so that it has a little bit of space for the hydrogen to bubble up past water level and actually ride up through. So you can see this is sort of shaped like I like to use the analogy of a Starbucks cup here, because gas will rise. So if the hydrogen collects here, it has an open pathway and it will gradually rise up to this 1/4 inch opening. And over here you can stick a pipe, and over here you can stick a tube and collect the hydrogen for measurement and eventually for a combustion chamber. But for experimental purposes, it'll be, of course, a measurement. But this should be a more efficient method for electrolysis and for electrolysis testing, and allow for really prominent research in green energy and the potential of using water to power our everyday appliances that we really couldn't before. If this design proves successful, or if it needs slight alterations, you could probably either make a really scaled up version, or depending on the effect of the length of this distance, this radius between the anode and cathode, depending on that, may need to make multiple of these cells and hook them up together.
So why do I need the Ingeniousplus grant to fund my research? Well, my school and mentors have been incredibly supportive. To fully test out my design, I need to purchase a 3D printer that's capable in printing in materials that can withstand the corrosive nature of sodium hydroxide, as well as various electrodes and a current limited power supply for safety and improved experimental uncertainty. With your help, I can test out the various electrode configurations, electrolyte concentrations, and runtimes to create the most efficient, cost-effective solution to green energy.